In this video, I'm going to be talking about a couple of related phenomena for gases called effusion and diffusion. Let's start with diffusion first. So diffusion is the term that we use when we're talking about mixing of gases. So for example, have somebody walked in at the back of the room and that person wears a lot of perfume. Perfume is a combination of gas particles. It takes a while for the smell of the perfume to reach the front of the room. That time that it takes for the perfume molecules to go from the back of the room to the front of the room is what we call the diffusion time. And it takes some time for the perfume to get to the front of the room because perfume molecules are mixing with the other gases in the room, primarily air. You remember when we're making the root mean square velocity calculation, we find numbers that are really high. But then we say it's in the mean free path discussion that the molecules themselves don't cover large distances, but then because the other gases are present, they start colliding with the other gases, making them travel only a very short path before collision happens. Diffusion time is important because there are a lot of times when we need to predict, for example, let's say you have a gas leak and you want to know how much radius of area do I have to clear out to make sure that everybody's safe from the gas leak. Those are all diffusion type related questions. Unfortunately, diffusion is actually quite difficult to calculate or predict because you have to take into account how the other gases behave. That makes it many variable type calculations, which makes things a lot more difficult. However, it's possible to estimate diffusion rate using a phenomenon called effusion. This is a much simpler version of gas traveling into a container. In effusion, the only thing you have to worry about is a gas going into a vacuum. So the only thing you're measuring is how fast does that gas travel into this vacuum container here. That you can do a quick experiment in, which looks something like this. Let's say you fill up the syringe, pull the syringe up and fill it up with a particular gas, let's say oxygen. And then you connect this through a rubber septum into a container that's already a vacuum. In other words, you've removed all the air here, let's say through using a pump. And what you do is you let that syringe slowly fill in the vacuum with the gases. And so what you see is that a particular gas would take a certain time in order to fill in that vacuum. So CO2 would take this much time, something like H2 would take a lot less time. And of course that tells you something about the speed, how fast these guys are traveling, because if it takes a lot longer to fill up that vacuum with that gas, that means that the gas must be traveling a lot more slowly. So the person who actually did this experiment back in the 1850s is Graham, and he was able to come up with this law equation to express the relationship of effusion rates between two gases. So the effusion rate of gas 1 divided by the effusion rate of gas 2 is going to be equal to the square root and the inverse of the molar masses of those two gases. So molar mass of gas 2 over molar mass of gas 1. Graham's law actually provides a really nice test for the validity of the kinetic molecular theory, because the kinetic molecular theory was developed around the same time. So the idea is that if using kinetic molecular theory we can derive Graham's law, that's yet another proof to show that in the kinetic molecular theory are valid ideas. And in fact, you can assume that rate should be equal to the root mean square velocity, right, which is the average rate of a sample of gas. And we have an equation for root mean square velocity that comes from the kinetic molecular theory, and the equation is root mean square of velocity of gas 1 is going to be equal to square root of 3 RT over molar mass of gas 1. Now this would be now our effusion rate. So effusion rate of gas 1. Effusion rate of gas 2 would be just this, which is square root of 3 RT over M2. You can then take a ratio of the rate of gas 1 over the rate of gas 2. The reason I want to do that is because that's what Graham's law is. It's the relationship of rates of effusion between two gases. So the rate of gas 1 over rate of gas 2 would just be the square root of 3 RT over M1 divided by square root of 3 RT over M2. I can make the entire square root over the whole expression here. You can see that once I write it this way, the 3 RT cancels out, and then I'm left with 1 over M1 over 1 over M2, which just simplified to square root of M2 over M1. We started with the kinetic molecular theory expression of velocity, and what we get at the end is rate of gas 1 over rate of gas 2 is equal to square root of M2 over M1, and that is exactly what Graham's law is. In practical terms, what is the use of Graham's law? Well, you can use it to do an estimate of diffusion rate. Here's an example. This is a common experiment that's done to demonstrate diffusion. So if I were to release some ammonia sample from this end, and I have another source of HCl here, usually these are just cotton balls. So you have cotton balls and they've been dipped in ammonia and HCl, and you just let them travel through this tubing that's filled with air. And what happens is the gases from the ammonia will travel and the gases from the HCl will travel, and eventually at some point they will meet, and when they meet there's a reaction between the two, and the reaction forms this compound, ammonium chloride, NH4Cl, which is a combination of these two species together. The distance where they meet depends on how fast the gases are traveling. You can see here they're meeting at this point, which is further away from here and closer to this side. What that tells you is that these guys are traveling more slowly because it doesn't cover as much of a distance, and then these guys are traveling further, right? Covers more of a distance. So in other words, this guy is a faster gas and this one is a slower gas. And that, of course, is what we expect because the molar mass of ammonia is 17 grams per mole, whereas the molar mass of HCl is about 36.5 grams per mole. So this one is a bigger particle, so it's going to travel less because its velocity is slower, okay? It's lower. Now, this ratio of distances, right, travel is the same as the ratio of the molar masses. So in other words, you can estimate using Graham's law. If I were just substitute this with molar mass of HCl and molar mass of NH3 and take a square root, what I get is a number that corresponds to about 1.5. If I were to do this experiment and I measure the ratio of these distances, which is this distance from here to here, and then over the distance from here to here, I get a number that's about 1.7, and that is very close, 1.5 and 1.7. The Graham's law case, we're calculating effusion rate. In this case, we're doing a diffusion experiment. So that's what the importance of Graham's law is. It allows us to get an estimate of diffusion rates. In practical applications of this concept, we usually need to estimate diffusion rate for various type of gases. So I just want to work through an example of how to incorporate the Graham's law, which is shown here. Rate of diffusion of gas 1 over rate of diffusion of gas 2 is equal to the inverse ratio of their molar masses. Take a square root of that. So I want to incorporate that into this problem, try to show you how to use that formula. Then what I want you to do is work on the second problem on your own. Okay, so let's get started. It says here that you have rate of diffusion of two gases. In this case, they're called Freon 12 and Freon 11. The ratio in this case is 1.07 to 1. That's the rate of 12 to 11. And then it tells you here that if the molar mass of Freon 11 happens to be this number, which of the following formula can be for Freon? You first have to get the molar mass of Freon 12 and then you try to match it to one of these formulas right here. So we got rate of, let's say, Freon 11 in this case, okay, over rate of Freon 12, and that should be the molar mass of Freon 12 over molar mass of Freon 11. So that's the way the relationship works for Graham's law. So you can then do the calculation here by just putting in your molar masses, right? So we got Freon 12. That's really the one that we're trying to figure out. So let's just symbolize that by X here. Then we got molar mass of Freon 11, which is 137.4 grams per mole, and equal to the ratio here. Now the ratio here that is shown is 1.07 to 1. That's for 12 to 11. We wrote it in such a way that it's 11 to 12, so then I have to invert that ratio, so it will just be 1 to 1.07. I can then square both sides of this equation, so then I'm left with X over 137.4 grams per mole on the left equals to the rate, which is just the square of that quantity, and then I just solve for X, and I get X equal to 120 grams per mole. Then what you'd have to do is find a molar mass that's closest to this for all of the formulas that are given here, and if you do that, you'll find that CF2Cl2 has that actual molar mass. This is actually common. You can do this in an experiment. Let's say you make a new gas and you're curious about what is the molar mass of that gas. So you can do it in an effusion experiment. You can kind of measure its relative rate to another gas of a known speed or a known rate, and then you just see what is the ratio of that, and that will tell you the molar mass of the unknown gas or the new gas that you just made. So that would be exactly the same approach like how you did this calculation. Okay, so in the last part here, I just want you to work through this problem. This is basically an effusion problem as well.